Let's go ahead and get started. I'm Dr. Jeff Ashworth. I am the instructor for the AE 420 Preliminary Aircraft Design for the first two presentations that you're going to see today. And we are very, very fortunate to have with us, maybe out here, to have with us on our panel from industry. As most of you are familiar with, they do not give their presentations, their final presentations, to the instructors that have been beating them up all this semester. They give their final presentations to a panel from industry. So what I would like to do, because we are very, very fortunate to have all of these technical experts with us today, is to pass the mic across and let them very briefly introduce themselves and let you know where they are coming from.
I'm Professor Bill Zwick here at Embry-Riddle. I teach preliminary and detail aircraft design.
I'm Chris Liebman. I'm from Edwards Air Force Base. I work at, right now I work at the F-22 Test Squadron. I'm the flight dynamics lead there. So performance, flying quality, structures, human factors, reliability, propulsion is kind of all my area. Graduated from Embry-Riddle in 2006 it was. Aeronautical Science and Aerospace Engineering, double degree, and then was a flight instructor at the flight line here at Prescott for 3 years. Came over to Edwards Air Force Base after that. So I'm excited. I've been there. You guys have a lot of pressure on you. It's okay. We'll get through this, I promise.
Edwards stole him from me.
Dustin Valentine. I'm a E-grad from 2008. I work at Institute now, aerodynamic and aircraft performance. A small team that gets a lot of experience with UAVs. So I'm looking forward to hearing your guys' presentations.
So my name is Connor Warren. I'm an aerospace engineer, graduated in 2015. Most of my work is in solid propulsion and integration. Currently out in the Mojave Desert.
My name is Bryce Melns. I'm an AE graduate from 2016. Right now I'm a structures engineer at Edwards Air Force Base, and I work on the F-35 program and the F-15 Saudi program.
Jacob Older. I'm an ERAU 2012 grad. I currently have about 4 years in industry with 1 year in project management.
Thank you. As you can see, we've got experts in about every area, which is absolutely fantastic for us, because what we do in this course is we don't start and design one little tiny piece of the airplane. We start off at the very beginning, and all we give them is the airplane has to do this, 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 and this with an RFP, with the performance characteristics of the airplane. And they start from that and design the entire aircraft. So what you're going to see today is we have the Reno Air Racer, which will be the first group, and then the second group is going to tell you how to go really, really fast and get people to a destination without any delay. So without any further delay, our first group is Chronos Aerospace.
All right, good morning everyone, and welcome. My name is Alexander Benz, and I'm the design team lead for Chronos Aeronautics. This will be our final preliminary design presentation. Throughout this presentation, the screen above me will be referred to as the primary screen, while the screen to your right will be referred to as the secondary screen. Without further ado, I would like to introduce the CA-1 Yellowjacket. The CA-1 Yellowjacket is a racecraft aircraft for an all-new IF-1 Plus category. You will notice the tail dragger configuration as well as the turboprop engine. I would now like to introduce the team. We will start out with Austin Gardner on performance and race operations, Vincent Arminio with CAD, Jason Ryan with weight and balance, Michael Byard with aerodynamics, Brian Ferguson with propulsion, Kelly Ramirez with stability and controls, and Ikedici Namdioso with structures and landing gear. I will now pass it off to Austin Gardner to discuss our background and motivation.
Thank you, Alex. So Reno Air Racing takes place at Reno State Airport in Nevada. It has a 7,600 foot runway and a 9,000 foot runway. Its elevation is 550 feet. There are many different types of aircraft that race here across 6 different classes and 4 courses. The IF-1 and biplane category course is outlined on the primary screen in purple. On the secondary screen is a picture of the Unlimited class and a picture of the home pylon, which serves as the start-finish line for all of the courses. So Reno Air Racing is, IF-1 Air Racing is a unique category in Reno in that it not only performs at Reno, it has tracks all over the world such as Europe and Asia. They are required to run the Lycoming 0200 engine, which produces just 100 horsepower. They must weigh 500 pounds empty and must run a fixed-pitched, 2-bladed propeller. A race is split up into heats with 8 aircraft performing on the course at once. On the secondary screen is a picture of the course, which consists of 2 straightaways and 2 turns. A race begins with all 8 aircraft sitting on the runway in their starting positions. The aircraft do not taxi to these positions. They are towed by trucks. When the race begins, all 8 aircraft take off and immediately fly into a scatter lap. When the first aircraft to complete the scatter lap crosses the start-finish line, the race begins for the entire field. A typical race is 8 laps in around 10 minutes. Aircraft accelerate along the straightaways and decelerate in the turns as they pull around 3.5 Gs. When the race is over, all aircraft pitch up and immediately fly into a holding pattern to land in their predetermined landing order. So due to the restrictions set by the IF-1 class rulebook, aircraft design has stagnated. This is illustrated by this past year when 2/3 of the entire field were just one type of aircraft, that being the Casset 3M. When the rulebook underwent its one and only major change in 1968, the category saw an increase in new designs and an increase in popularity. We wish to mirror this. We are proposing key rule changes in order to increase design diversity and update performance to a modern standard. This will also have the secondary effect of leading to additional sponsorships to allow money to flow through this category more easily. On the secondary screen is our proposed rule changes. These rules make up the only major changes to the rulebook that we are making. We are removing the Lycoming 0200 aircraft engine requirement and allowing for any engine that drives a propeller. We are removing the 66 feet squared wing area and the 500-pound weight limit. The 66 feet squared represents a minimum wing area. Finally, we are removing the 2-bladed fixed pitch propeller requirement and allow for new designs and new materials. In order to verify that these rules will update and increase performance of the class, Chronos Aeronautics has designed the Yellowjacket. To begin our project, we took a look at current and past IF-1 race planes, the first of which is the Sharp Nemesis. This aircraft is considered the most successful race plane of any category of all time. It won 45 out of 47 races it ever competed in and competed from 1990 to 1999. Its lap time record of 42.54 seconds still holds this day as the category's lap time record. Another aircraft that we took a look at was Pushy Galore, a unique pusher-style design, and a current Casset 3M racer, that being Quad Nickel Racer. I would like to hand it off to Vincent Arminio to discuss aircraft configuration and design.
Thank you, Austin. For the configuration of our aircraft, Chronos Aeronautics decided to go with the tractor configuration, with a propeller in the front and an empennage in the rear. This is due to the fact that tractor-configured aircraft tend to have better engine performance and are typically easier to design due to the fact that there is a greater amount of design source material catered towards tractor configurations. On the secondary screen are 2 alternative configurations. These are the mixed and the canard type configurations. Both of these configurations were considered and we ultimately went against. On the primary screen is a 3 view of the CA-1 Yellowjacket. Some basic dimensions are a wingspan of 19 feet 4 inches, a length of 16 feet 3 inches, a height of 5 feet 9 inches, a tail span of 5 feet 3 inches and a propeller diameter of 5 feet 7 inches. In designing the Yellowjacket, it was necessary to first consider visibility restrictions set forth by the IF1 rulebook. The Yellowjacket has a visibility of 5.4 degrees below horizontal over the front cowling of the aircraft and 25 degrees below horizontal over the leading edge of the wings. On the secondary screen, you'll notice that the Yellowjacket meets both restrictions with respect to visibility set forth by the IF1 rulebook. In designing the cockpit of the Yellowjacket, we first considered a general seating position of our pilot. Because the IF1 rulebook does not restrict cockpit dimensions, we then designed the cockpit and fuselage to fit snugly around the pilot. On the secondary screen is a picture of a current IF1 aircraft. You'll notice that the pilot is fit snugly within the cockpit. This snug fit is typical of many race planes, especially those in the IF1 category. So, as already mentioned, the IF1 rulebook does not restrict cockpit dimensions. However, in designing our cockpit, we look to recommendations for home-built aircraft as a starting point for our design process. The Yellowjacket has a length and a distance between the control stick and the back of the pilot, which matches those recommendations for home-built aircraft. However, for the width of our cockpit, we decided to compromise on a little bit of space within the interior of the cockpit in order to create a more aerodynamic profile. On the secondary screen is a ghosted view of our cockpit from a top-down view. In designing the front of our aircraft, we first considered the engine placement of the engine. The cowling was then designed to fit snugly around the engine while maintaining an aerodynamic, streamlined design from the front to the rear. This designing the front cowling was made relatively easy due to the fact that the dimensions of our engine are relatively compact, as is evident on the secondary screen. Because the Yellowjacket will be transported to and from races, it was necessary to design the Yellowjacket to have removable wings. This was done by implementing a double lap splice mechanism. As is evident on the image behind me, 2 double lap splices were attached directly to the roll cage on either side of the aircraft. In order to remove the wings, 3 bolts are removed from the interior of the aircraft, and the wings are simply slid out from their respective slots. On the secondary screen is a close-up view of one of our double lap splices. For the landing gear design, we went with a fixed landing gear type of the tail dragger configuration. Our main gear is comprised of 2 struts and 1 wheel per strut. Each strut is of a symmetrical airfoil cross-section in order to reduce on drag, and each wheel has a aerodynamically designed tire fairing in order to reduce drag. For the tail gear, the wheel was embedded into the fuselage, also in an effort to reduce drag. The Yellowjacket has a tip-over angle of 16.65 longitudinally and 29.29 degrees laterally. As you can see on the secondary screen, both requirements with respect to tip-over angle have been met. For the propeller clearance, we have a dimension of 8.38 inches. Though a 9-inch clearance is recommended, we decided that compromising on this clearance a little bit was necessary in accommodating a propeller of the appropriate diameter. For the tail down angle, we have a dimension of 15 degrees, which meets the recommendation. Next, I'd like to introduce Jason Ryan, who will be covering weight and balance analysis.
Thank you, Vincent. The weight and balance analysis of our aircraft C-81 Yellowjacket begins with an individual component's weight and CG location estimation. For example, the fuselage, wing, vertical tail, and horizontal tail CG location and weight were estimated using the methods found in the Roscom text. On our secondary screen, you will observe the coordinate system that was used in the weight and balance analysis. Our x-axis is measured from the nose of the aircraft. Our y-axis is measured from the center line of the aircraft. And our z-axis is measured from the bottom of the wheel of the aircraft. Now on our primary screen, you'll observe the center of gravity location calculation that was done for our empty weight. And on our secondary screen, you'll observe our center of gravity location calculation that was done for our takeoff weight. The most important things to take away from these two slides are going to be our empty weight of 504 pounds and our takeoff weight of 722 pounds. Now on our primary screen, you'll observe our race center of gravity excursion diagram. Our x-axis is defined as our CG location with respect to our mean aerodynamic chord, and our y-axis is going to be our weight of the aircraft during our race. Starting with the furthest red point to the left, following the red arrows to the right, we're going to have our pilot and fuel on board, leading us to the most aft CG location, defined as our takeoff weight. And then we're going to be following our blue arrows to the left, where we're going to be using our fuel during the race, and have our pilot take off after the race is over. The linear relationship that you see in our excursion diagram comes from the fact that we do not have any passengers or baggage. We also have the aerodynamic center of the aircraft plotted in this diagram in order to show our static margin of 5.5%, which is going to be the distance between the aerodynamic center of the aircraft and the most aft CG location. And on our secondary screen, you'll observe our most forward and aft CG location that was found in our weight and balance analysis. Now I'd like to pass the floor over to Mike Byer to discuss our wing design and aerodynamics.
Thank you, Jason. For the airfoil of our Yellowjacket's wing, we have selected the NACA 63212. As you can see on the primary screen, 63212 is a fairly thin cambered airfoil. On the secondary screen is a CAD representation of the Yellowjacket's wing using this airfoil. Now on the primary screen is 2D lift data for our airfoil. The 63212 has a maximum lift coefficient of 1.19, an angle of attack where lift equals 0 at 2 degrees, negative because it is a cambered airfoil, and a gradual stall region. This gradual stall region is important to us because our race takes place at low elevations and near a crowd. A stall in this condition could have potentially catastrophic consequences for both our pilot as well as spectators. The gradual stall region gives our pilot more time and a greater range of angle of attack for which to recover from a potential stall. On the secondary screen is 2D drag data for our airfoil. Now, this is taken directly from the fundamental airfoil data and represents wind tunnel testing. As such, drag here is comprised both of skin friction drag as well as pressure drag due to separation. The maximum drag coefficient for this airfoil is 0.0198. However, during race configuration, we'll be seeing drag much less than this. For our wing design, for our aspect ratio value, a larger value was desirable to reduce the effects of induced drag on our aircraft, while a lower value is desirable for structural constraints, as we will be pulling higher G maneuvers. A value of 6 was selected based on the recommendations of the Roscom text, as well as an analysis of previous aircraft. For our wing area, we have just over 60 square feet, which is notably less than the previous minimum requirement set in the IF1 rulebook. This area was selected based on our design point and our maximum takeoff weight. Our as-well sufficiency factor was calculated for our specific wing geometry to be 0.833. Our incidence angle is set to 0 degrees because with a cambered airfoil, we have sufficient lift in this configuration. And our taper ratio of 0.45 and dihedral angle of 3 degrees are set based on recommendations of the Roscom and Raymer texts. On the secondary screen is a sketch of our plan form. As you can see here, we have a small leading edge sweep. This results from our taper ratio, aspect ratio, and having our quarter chord sweep set to 0. The aileron shown on this plan form is approximately 41 inches long and takes up 21% of our chord. Analyzing the effectiveness of this aileron, we calculated the maximum roll rate of the Yellowjacket to be 256 degrees per second, given a maximum aileron deflection of 25 degrees. Also of note on this plan form is we have not included flaps or other high lift devices on our rig. As a small, lightweight race aircraft, we have sufficient lift for our race phase, and these devices will only serve to add weight, drag, and complexity to our design. Converting our 2D airfoil data to our 3D wing, we see a reduction in our lift curve slope and a reduction in our maximum lift coefficient from 1.19 down to 1.07. This is accompanied by a small increase in our stall angle of attack from 11 to 12 degrees. Converting one more time from published values given at Mach 0.2 to our race velocity at Mach 0.4, we see another reduction in maximum lift coefficient from 1.07 down to 0.76, while maintaining our lift curve slope. Now it's important to note here that during our race, our maximum angle of attack required is less than 5 degrees. So the second conversion down from Mach 0.2 to Mach 0.4 will not hinder our race performance. On the secondary screen is the tabulated values that I've just mentioned. Because we have elected not to include high lift devices on our wing, an analysis was made to verify our landing and takeoff distances. With a stall velocity of 61 knots, our takeoff distance is just over 900 feet, and our landing distance is just over 2,000. These are both well within the dimensions of the runway at Reno and other race airports. For the drag breakdown of our aircraft, two methods were used to compute the parasitic drag contributions. One for the lifting surfaces of the Yellowjacket, based on using our drag data I presented earlier from wind tunnel testing, and a second method using form factors based on our components. Using our CATIA model, we measured frontal and wetted areas of our major components and applied their form factors to find their parasitic drag contributions. Additional factors on this table include form factors of our landing gear, our canopy, as well as engine cooling drag. Now on the primary screen is our combined drag during our 1G flight, which is experienced during the straightaways of our race. As you can see on the right side of the graph, at our race velocities of near 250 knots, our drag is almost entirely comprised of parasitic drag. As such, efforts were made throughout our design to reduce this. These efforts include adding fairings to our main landing gear, adding aerodynamic cross sections to the landing gear struts, and embedding our rear landing gear into the fuselage. On the secondary screen is our combined drag during our 4G turn maneuver. This drag is, as you can see, is greater, as the 4G turn is a higher energy maneuver requiring more lift and creating more drag. Next, I'll hand the floor over to Brian Ferguson, who will discuss the selection of our propulsion system.
Thank you, Mike. We began our engine selection process by looking at the current engines used in IF1 races. This engine is the Lycoming O200 engine, which produces 100 horsepower, weighs 170 pounds, and was designed over 70 years ago. This couldn't get us close to the performance levels we desired, so we considered larger naturally aspirated engines like the Lycoming O300 and O360. These have an increase in horsepower, but a massive increase in weight. Therefore, we turned to more unique alternatives that had not been previously permitted within the IF1 rulebook. The engine we selected was the PBS TP100 turboprop engine. This engine produces 241 horsepower, weighing 135.8 pounds, and was designed in 2013, bringing a much-needed update to the sport of IF1 racing. On the secondary screen, we can see a picture of the engine itself. Note that its small engine housing almost fits entirely behind the spinner of the propeller. The propeller the Yellowjacket will be using will be a four-bladed constant speed propeller. The constant speed propeller option was selected because it allows the engine to operate at the RPM associated with its maximum continuous power output, while also being used by other high-performance race planes within the Reno air races. The diameter of our propeller will be 5.6 feet, spinning at 2158 RPM, leading to a tip speed of 766 feet per second. On the front of the Yellowjacket, an inlet was designed to take into account the necessary mass flow rates for engine cooling, nacelle cooling, as well as the mass flow rate for the engine itself. This led to an inlet area of 76 square inches, and when compared to a similar aircraft that had been retrofitted to use the same engine, it compared very favorably. On our secondary slide, we can see a fuel breakdown during our mission. We burned 33¼ pounds of fuel, with the majority of this fuel being consumed during our race phase, in which the engine is operating at a high power setting. Now, the maximum continuous power our engine can produce is 214 horsepower at sea level, but at our race altitude of 5,200 feet, we only have 196 horsepower available. On the secondary screen, we can see our power available with altitude. Note that the lines are straight due to the constant assumption that is made when analyzing propeller aircraft. Now, when we take our power available and our power required for a 1G maneuver, we can get a better sense of the performance of the Yellowjacket. What it shows is that the engine we selected produces adequate horsepower, leading us to a top speed of 251 knots while having a maximum excess power of 6,500 feet per minute. On the secondary screen, our power available and our power required for a most demanding 4G turn around the pylons. This is a higher energy maneuver which has risen the power required curve upwards, reducing our top speed to 227 knots, as well as our maximum available excess power to 2,700 feet per minute. Now we combine our drag data from earlier and our propulsion and performance data. We developed a race time calculator to see how the Yellowjacket race plane would stack up against current and past IF1 racers. How this calculator worked was by breaking the track up into 2 turns and 2 straightaways and determining the time to complete each segment. What it showed was that our Yellowjacket race plane could complete a lap of the IF1 race course in 39.28 seconds. And this is 9 seconds faster than the typical cassette 3M racers used today, and still more than 3 seconds faster than the Sharp Nemesis, which is the fastest IF1 race plane to ever compete. This means over the course of an 8-lap race, we'll be lapping the cassette racer more than once and still finishing more than half a lap ahead of the fastest race plane ever to compete in IF1 racing. This is due to the fact that we chose a modern, high power-to-weight ratio turboprop engine that can now be utilized in the new IF1 Plus racing category. When we look at our specific excess power for the Yellowjacket for a 1G maneuver and at our race altitude, we can see that the Yellowjacket race plane runs out of excess power, leading to our top speed of 251 knots. And on the secondary screen, during our 4G maneuver around the pylons, the Yellowjacket runs out of excess power at a race altitude at 227 knots. The flight envelope for the Yellowjacket is bounded by the curved stall lines, the vertical top speed lines, as well as a 6G and -3G operating G limit. This is the flight envelope in which the Yellowjacket will be operating within the race. With that, I'd like to introduce Kelly Ramirez to talk about our empennage design and the stability of the Yellowjacket race plane.
Thank you, Brian. The empennage is designed using a conventional configuration. A conventional configuration involves the vertical and horizontal tail to be attached at the tapered end of the fuselage. This configuration provides adequate stability and control at the lightest structural weight. On our secondary screen, we have a 3D CATIA model of our empennage. The horizontal and vertical tail were designed using an initial estimate given on the Roskin text. From there, we analyzed these parameters and verified using longitudinal X-plots and directional X-plots. For the horizontal tail, we use a NACA 63012 airfoil with an area of 6.88 feet squared and a span of 5.25 feet. On the right side of the primary screen is dimensions of the horizontal tail with the elevator. On the secondary screen, we have our horizontal tail lift curve slope. This shows a clean horizontal tail configuration and also a 25-degree deflection elevator configuration. As you can see here, the CL max increases with a 25-degree deflection and shifts to the right. On our primary screen shows a 3D CATIA model of our elevators. On the secondary screen shows important parameters of the elevators, such as the elevator takes 36% of its total platform area of the horizontal tail. Also a max deflection of 25 degrees. The vertical tail uses a NACA 0012 airfoil with an area of 3.35 feet squared and a span of 2.24 feet. On the right side of the primary screen shows diameters of the vertical tail, including the rudder. On the secondary screen shows a vertical tail lift curve plot with a clean vertical tail configuration and a 25-degree deflection rudder configuration. Here we have a 3D CATIA model of our rudder. The rudder uses about 37% of the total platform area of the vertical tail and also has a max deflection of 25 degrees. Moving on to stability and control. On the primary screen shows our longitudinal X-plot, which graphs the aerodynamic center and the center of gravity with respect to the horizontal conform area. The distances between these two lines is referred as the static margin. For the Yellowjacket, the static margin is 5.5%, which is considered desirable. On the secondary screen, we have our longitudinal static stability plot, which plots our coefficient of pitching moment with respect to the angle of attack. Here we have a negative slope, which is considered desirable. Therefore, the aircraft at high angle of attack would want to pitch down back to trim conditions. On our primary screen shows our lateral static stability plot, which plots our coefficient of roll moment due to side slip. Here we have a negative slope, which is considered desirable due to the fact that the aircraft would want to roll back to pitch conditions relative to the wind. On our secondary screen is our directional static stability plot, which plots our coefficient of yaw moment due to, with respect to the side slip angle. Here we have a positive slope, which is considered desirable due to the fact that the aircraft with a high angle of side slip will want to yaw back to the right to trim conditions relative to the wind. Therefore, the Yellowjacket is considered stable. I would like to hand it off to Ikedici, who will be introducing structures and material of the aircraft.
Thank you, Kelly. In order to maintain structural integrity and provide rigidity to the Yellowjacket, it was necessary to include internal reinforcements within the model. This was done using recommendations from design textbooks like the Roscom and Waymo text, and also observations from other aircraft. The secondary screen shows the full internal structure for the Yellowjacket. For the structural sizing of the wings, two spars located at 15 and 75% of the wing chord respectively are used. A rib spacing of 36 inches with additional ribs included for aileron attachment points is implemented. High density foam core will also be utilized in between the ribs and spars for additional rigidity. The secondary screen shows the internal structure for the Yellowjacket wings. For the structural sizing of the empennage, the horizontal tail has spars located at 13 and 37% of the horizontal tail chord, while the vertical tail has a single spar, vertical spar, from top to bottom located in front of the rudder to avoid interference. For both of these surfaces, a rib spacing of between 15 to 20 inches is used, while also ensuring that additional ribs are placed for control surface attachment points. High density foam core will also be used in between the ribs and spars for additional rigidity. The secondary screen again shows the internal structure for the Yellowjacket empennage. For the fuselage, frames that are 1.5 inches in depth, between 0.375 and 0.5 inches in thickness, with a frame spacing of 20 inches are utilized as per recommendations from Roscom text. Within these frames, a roll cage will be used to reinforce the aircraft. This roll cage is a basic truss structure comprised of round beam members. Roll bars attached to the roll cage behind the canopy to support the canopy and also protect the pilot. The secondary screen again shows the internal structure for the fuselage. The primary screen shows a cutaway view of the CA-1 Yellowjacket. Note that there is no interference between any of the internal structure being used. Having selected internal structure, it was necessary to pick materials for all these structure. Using the limit load factor of 6 Gs from the RFP, an additional 1.5 factor of safety brings an ultimate load factor of 9 Gs. Using this ultimate load factor, ultimate wing and empennage loads were calculated using the lift equation and a sum of moments about the aircraft center of gravity respectively. Using this ultimate loads, bending stresses were calculated using an idealized beam section theory, where the wings and the horizontal tail were approximated as idealized wing box sections. For static loads, the main gear was modeled as a beam in bending, with the maximum moment being taken about the landing gear attachment point to the fuselage. The secondary screen shows the results of these bending stresses. These values were used as a basis for selecting the materials of the Yellowjacket. Having selected materials, it was necessary to go back to validate the structural integrity of the wing attachment. The spar failure analysis was used unidirectional carbon fiber material properties to check the bearing, tear out, and tensile failure modes. A minimum margin of safety of 2.01 was found, showing a failure will not occur. For the bolts, a shear failure mode was considered. A margin of safety of 18 was found for a 1-inch diameter bolt, steel bolt. The primary screen shows the major materials used by the Yellowjacket. Carbon fiber is used for all ribs and spars due to its high strength and low weight. Aluminum 6013 T6 is used for the fuselage frames and roll cage. This was selected to be able to withstand the same stresses as the wing ribs and spars as per recommendation from the Weymouth textbook. Polyurethane foam will be used for all foam cores due to its high density and also low weight. All these materials, the density for all these materials was found, and a total structural weight shown on the primary screen of 451 pounds was calculated. This brings a total structural cost shown on the secondary screen of about 4,620 pounds. It is important to note that this information is gotten from the CES EduPack software and is strictly for raw materials. It does not include manufacturing costs or maintenance. Next, I would like to reintroduce Alexander Barrett, who will be going over the full cost analysis.
Thank you, Ikedici. Looking into the total cost analysis for the Yellowjacket. We started off by looking at the RDT&E cost for the Yellowjacket. Initially, we decided to use the Roscom, Raymer, and Nikolai tests to determine the RDT&E cost. However, these methods assume production aircraft and gave us unrealistic values for our one-of airplane. So to get these values, we looked at our estimated costs from this semester and applied that to next semester as well, and added the two values together to get our cost for RDT&E. Moving on to raw materials, Ikedici previously mentioned our cost for the raw materials. The value shown also includes a one turboprop engine of $110,000. Moving to manufacturing, the manufacturing cost was determined from a similar IF-1 racecraft of a similar weight. We just determined that because of this, that this manufacturing cost would be applicable to our design. In addition, a spare engine was considered, as most race teams have a spare engine on hand during the races. This brings us to a total for this part of $480,000. Moving on to the M&O and total LCC cost, a maintenance cost of $26,100 was estimated for our 10-year life cycle, as well as a fuel of $8,400. Note that these values are fairly low because of our low race times and the fact that our aircraft will only be racing a few times a year. This brings us to a total here of $34,500 for proposed cost, and a total life cycle cost of $514,000. Looking at the Chronos Aeronautics labor hours, You'll notice that 35% of our time was spent on professional development, where coming in second, we have administrative costs of 23%, coming to 525.75 hours. You'll notice on the secondary screen, the line in black projects the minimum required hours for this class. The black line is based on 2 hours for every hour in class. The green line shows Chronos Aeronautics' current hours. Because the green line is above the black line, the minimum hours required for this class have been met. Moving on to the distribution of the total costs. 36% of our cost was attributed to professional development, coming in first, and in second, 28% was accounted for as engineering. Adding all these costs together, we have a total cost of $110,735 for the team. Moving on to our conclusions and recommendations. In conclusion, drag while racing is dominated by parasitic drag. This was a key design factor which allowed us to make adjustments to our design as we move through the design process. In addition, the PBS TP100 engine contributes to the Yellowjacket's competitive performance capabilities, which will allow it to introduce this IF1 Plus aircraft racing configuration. Also, we determined that the CA1 Yellowjacket is statically stable in all 3 axes, and composite ribs and spars and structure at a low weight cost is going to be beneficial to the overall design. Also, the current design choices allow for a very quick lap time that is competitive to current IF1 race aircraft. Moving to recommendations on the secondary screen, you'll notice that we would like to consider additional ways to decrease the lap time of the aircraft. This may include possibilities such as reducing the structural weight and finding other ways to reduce the overall drag of the aircraft. We'd also like to perform a more in-depth structural analysis of the structures for the aircraft. We'd also like to start conducting wind tunnel testing to confirm our preliminary data. And we'd also like to work on general construction of composite aircraft research. At the moment, we are not, we would like to look into general construction of these types of aircraft. I will initially field any questions. Thank you everyone for your time.
Okay, so we have about approximately 15 minutes for questions now, so I'll pass the mic along to our evaluator.
Okay, nice job, guys and gals. Excellent work. Really innovative project. I'm going to direct my questions in 2 different areas. First is, you guys correctly identified parasitic drag as a big deal. And you talked about your landing gear design as, addressing that. But the overall wetted area is a huge contributor to parasitic drag, as you guys all know. But I didn't see anything in your presentation about what you would do to minimize form drag on the wing surfaces, control surfaces, and things like that. So I think some attention to that would be well put. The other thing that I noticed is that vertical tail and the rudder looks really small. And generally, if it looks small, it might be. Now, I know that you took a lot of advice from Roskin and Raymer in sizing those, but my concern is that with that turboprop engine swinging a huge prop on the front, the P-factor effect during takeoff is going to require a lot of rudder to counter that. Also, you're going to need a lot of rudder for crosswind landings and things like that. So you might want to consider reevaluating your rudder size. I have a bunch of other comments in my presentation, but in the interest of time and to let the other evaluators ask some questions, I'm going to pass it on. Do you guys have any comments, feedback on my comments? Yeah, Kelly.
So the rudder did account for a crosswind of 20 knots.
Okay, good.
The IF1 rulebook states that a 20-knot crosswind would discontinue the race.
Okay.
So we considered a crosswind requirement of 20 knots.
Very good, excellent. Okay, good. Okay, thanks.
All right, you guys obviously put a lot of work into this, so high five. However, I've got a couple questions because that's my job. So, slide 29-ish, you mentioned that I think it was your cruise alpha was going to be 5 degrees. And I'm curious, 5 degrees, is that 1G flight or is that in elevated G flight? And what G condition was that at?
Yes, that'd be a question for our aerodynamics person. Yeah, sorry for the confusion. What I meant to state is that during our race, our maximum angle of attack required to like pull our forward G remover is less than 5 degrees. We don't actually get to 5 degrees angle of attack required for our lift. So what I was saying is that due to our decrease, there being no change in the lift curve slope, the second reduction of maximum lift won't hinder our performance.
Okay, so you're saying that even at 4 Gs, you're going to be less than 5 degrees alpha?
Yes.
Okay. And then, so how does that figure in for landing? So I'm guessing you're going to land slightly slower. What kind of alpha are you talking about there?
Yes, our CL required during landing is just around 0.76, which at landing, we don't have to take into account that second reduction in our lift curve slope from Mach 0.2 to Mach 0.4 at our stall velocity of 61 knots. So you're just over that when you're landing. So we'll be using that blue curve shown on the graph there during our landing configuration, which will still be away from our stall condition.
Okay, so you're somewhere around 7-ish alpha, that's what I see.
Yes.
Okay, good, that helps me, thank you. So my next question is in only 4 parts, but it's not as bad as it sounds. So I'm going to ask 4 questions, and then we'll kind of come back, and there's kind of a bigger thing I want to talk about. So, and if you would follow along with me, slide 15. So you said that you're going to make your design cockpit narrower than the recommendation by, it looks like 4 inches. How does that compare? So there exists kind of data on what normal human sizes are. Did you look at all in terms of the size of normal humans and whether or not that 1 foot 8 inches is actually going to work? That's question 1. I'm going to go through all 4 and then we'll come back to it. Slide 20. You decided that you had a need to reduce your prop clearance by, I think it was about 0.6-ish inches, because it was supposed to be 9 inches. I guess what I'm curious, what flight condition does that impact, or what are the implications of reducing that? You had a design need for it, but there's the compromise side. So what are you giving up, is my question. On slide 24, you had the CG shifting, I think it was 4% Mach forward as a result of fuel burns. So it went, you're burning almost all your fuel, and I'm curious what the implications are of having that CG move forward as you're racing. And are there any handling qualities implications that are coming out of that? And final thing, you have a gradual stall on slide 27. And if you have a really gradual stall, that's cool. But what I'm curious about is, will your pilot know that the airplane is stalled? Are you planning to have a stall warning system, that sort of thing? So what are the implications of having such a gradual stall? I think what I'm trying to get at in general is I'm really glad that you were able to document and you recognized some of the advantages of your design, but also talk a little bit about some of the drawbacks or some of the compromises. And what I think you're probably going to end up saying is that you're putting more workload on the pilot with each one of those design compromises. And at some point, we have to care about the pilot and all the workload that we're putting on it, because we're already putting him in a really high stress situation of trying to get trying to really max perform the aircraft and cut pylons as close as possible, and you're doing it awfully close to the ground. Adding all of those extra workload increments is going to be a challenge. So if you want to respond to any of those 4 questions, go ahead. But that's kind of all I had to say. So thank you again.
All right, thank you very much. Actually, for your first question, I want to say that we did take a look at actual physical seat that's used in some racing applications, and so some dimensions were taken initially from that seat. So that's the one I have for that. Your second question that you had about the, I believe the propeller strike. Yes, so for that, we determined, I believe it's 11 degrees down until the prop was for a prop strike. So we did, take a look at that as possibility of something that would be negative that would occur.
Okay, so what I'm getting at, and great, what I'm getting at is, okay, but what does that mean? So the prop strike thing, what does that mean? When are you most likely to get the prop strike condition? And I'm thinking that it's probably max braking, but it might also be some kind of landing condition. That's kind of where I'm getting at, is think about the flight condition, think about what scenario would cause that particular constraint to be tested or to be stressed.
Okay.
So I have several questions as well. Probably not as in-depth as Chris, but so the propeller, did you guys size the propeller? Did you guys just take the engine manufacturer's recommendation?
This is a question that Brian would love to answer.
So the propeller that the engine comes with is a 3-bladed variety that is 6.2 feet in diameter, but being that we didn't want to have this thing on stilts, which would increase our form factor drag that Professor Zwick was earlier talking about, we used the equations found in the Raymer textbook, which uses a K factor, and 4 blades to then, for our K factor and our power, which was the power from our engine and then our power that had been adjusted for our flight altitude, to then size the diameter of our propeller.
Okay. General Raymer adjustments. So when you're changing, I guess the question is when you're changing diameter of the prop, are you reevaluating the power condition that you're operating at through cruise and?
Because we have an unconventional mission profile, we're pretty much always at full power. So cruise and those more traditional phases in like a cargo or airliner style plane didn't really apply to our aircraft. So we always assumed max power.
Okay. And then did you look at a fixed pitch versus variable pitch for the weight consideration, and how much impact did the variable pitch add to the gross takeoff weight?
Yes, we did. So starting off with our initial weight estimates, we allocated weight for this, knowing that we'd have a more complex mechanism. Then as we started getting more detailed through research, we found for small, lightweight variable pitch mechanisms, we found between 25 and 32 pounds. We have 28 pounds allocated to this mechanism, as well in performing a propeller analysis using a propeller design tool that one of the air professors on campus has designed himself, designing a propeller for 2 different conditions, one fixed, one varying. We saw that there was a 20% increase in thrust at our takeoff velocity, which then resulted in a 8% decrease in our takeoff distance. So these were factors taken into consideration, as well as inspiration from other similar aircraft that race in other categories.
Thank you. Okay, so the next question is, so it was a little unclear to me, is what components were composite and what components were aluminum? The empennage concerned me a little bit as well. And then you only had one spar on your vertical? So during your flight conditions, I guess, how much loading are you seeing on your vertical tail, and are you expecting to see any resultant angle increase due to rotor deflection?
Okay, so for your first question, aluminum is made solely the fuselage, internal structure, the low cage and the bulkheads or frames, and also the firewall. There was not enough time to put all the materials in the presentation, but yeah, aluminum is mainly the fuselage, internal structure, and the firewall. Well, everything else is made up of composites. For the other questions you had about the vertical tail, yes, it has one spar due to the size of the elevator, so there wasn't much space to put in another spar. So the high density foam core might help, but that's why we added in our recommendations that we would like to do a more in-depth structural analysis, because for this semester, the preliminary part, It was just a rudimentary structural analysis that was part of the prelim. Details where we do a more in-depth structural analysis. But yeah, that's a very good point.
Okay, good presentation. Thanks, guys.
All right, well, you said good presentation, so I'll just say that again quickly. So, slide 11. I got a bunch of questions, but some of them have been covered already, so we'll try to go quick. So what was your criteria for configuration? Did you guys make like a criteria matrix? Did you guys decide on what you could realistically build here? Like, how did you figure out that the tractor configuration was the best configuration?
Yes, so we actually, when we decided this out, initially we looked at designing a design matrix, or sorry, a decision matrix. This, and we laid out all the positives and negatives of each configuration, and ultimately made the choice to go with the tractor configuration.
Okay. Yeah, I know you're trying not to over-inundate us with information, but I think that would have been good to have one, just personally. All right, slide 26A. This is kind of just a repeat of that question. It's how did you select this airfoil? Just same comment. Slide 36. There we go. I can't remember who was presenting this section, but the presenter said compared favorably, and maybe I missed that, but how did it compare favorably?
Yes.
Sure thing. So I used inlet sizing diameters out of the Nicolitex. So calculating this inlet area, I compared it, extrapolated it to an equivalent. Ours is an odd shape. Extrapolated it to the equivalent circle, and that way then I looked at other aircraft that have been retrofitted, because this is a very common engine to install in small lightweight aircraft because of its high power and low weight. And doing the measurements on the screen, it was very similar.
Okay, that makes sense. I just didn't know what you meant. Slide 15, please. So kind of hitting on this point again. What was your material selection process? This is something that's always important to me because materials can determine a lot of things that you don't think about. For example, carbon fiber doesn't like RF frequencies, just as an example. So it would be nice to see that criteria matrix, how you guys came to that decision for those materials. I'm not saying it's wrong or anything like that, it's just it would have been nice to see, but it looks like you guys did consider a wide range, because I'm seeing foam, I'm seeing e-glass, I'm seeing carbon fiber. You guys thought about it. It'd just be nice to see how you guys thought about it. Slide 64.
Last question.
I know, I'm doing not doing a good job. This was good to see. Thank you guys for putting all this at the end, because that caught me back up. But overall, good presentation, you guys.
I'm just gonna echo that a little bit. You guys did a great job. I'm gonna run through this really quick. Let's go to the structure slides. So let's do 51, and I'll just kind of talk from there. So that, I know that you guys did a rudimentary structural analysis, like you said. It doesn't really seem like enough to withstand that 6Gs you guys are talking about, or the 9G ultimate. Someone already had a comment about the vertical tail. I think from one thing I would like to see is your bending stresses. Put the materials section before that, because it was kind of confusing to me, because you have to have materials to get stress. So having that after kind of threw me off. And the last thing, correct me if I'm wrong, are you guys planning on routing a lot of the load through the skin of the aircraft? Because based on the way that you have the wings and the empennage range, that kind of looks like what you're going for. Is that correct?
Yeah, one second. I know Austin actually has a good answer for that.
So with this aircraft being mostly a composite aircraft, a lot of the loads will be taken by the composite skin as well as the foam cork, with the frame acting as stiffening and also taking some of the loads. Here we don't have pictured the skin or the foam in order to allow for detail to be shown on the structure.
Okay, thank you. Just so you're aware, you're probably going to need another spar on your vertical tail, regardless of what you think at this point.
Yes, sir.
This is just for answers. Thank you guys, great job.
like to echo what everybody else has said so far. Very, very nice job. I'll keep this short, as most of my questions have already been asked and answered. We'll just move right along to slides 62, 63, just on the management side. I just have a quick question. How are you defining professional development?
Yes, so professional development is spent on expanding our own individual knowledge. So I encourage my team throughout the semester that if they don't know something or aren't 100% sure about something, because this is in a classroom environment, I wanted to make sure that they understood what they were doing before they went through and did the process of something, to make sure that we would also get the most accurate results, as well as the fact that they're expanding their knowledge on certain topics.
Okay, I only ask because usually in industry you would just define that under engineering. But I understand this is a classroom environment, so there's a bit of a different definition there. I just wanted that to be something that y'all are aware of as well.
Okay.
But very nice job, thank you.
All right, thank you.
Okay, thank you very much, guys. Good job. And so we'll take a quick break right now. We'll come back at basically a quarter after, and we'll start with our high-speed group.